Unit 8, Chemical Bonding, pages 166 to 170, an intro to chemical bonding. Valence electrons and Lewis symbols. Inner core electrons are pulled so close to the nucleus that they do not participate much in chemistry. The outer shell or valence electrons are responsible for most chemical behavior. The reason why chemistry is similar in the same group or column of the periodic table is that all of the elements in the same column have the same number of valence electrons. Elements in the columns of the periodic table have the same number of valence electrons. These electrons greatly influence the chemistry. So there's the summary of what's important from there. Elements in the columns of the periodic table have different core electrons. These electrons have only a small effect on the chemistry. So the electrons that are farthest from the nucleus are going to be the ones responsible for chemical bonding. Writing a Lewis dot symbol. Beryllium has the following electron configuration: 1s2, 2s2. The 1s electrons are the core electrons, and the 2s electrons are the valence. These are the ones on the outer energy level. So we only focus on the valence electrons. So here's the noble gas configuration, helium 2s2. Here's our valence. Since there are two valence electrons, a Lewis dot symbol would be the symbol for beryllium and then two dots to represent the two valence. Writing Lewis dot symbols. The alkali metals have one valence electron. The noble gases on the right side of the periodic table are where the shell fills with 8 electrons. To find the number of valence electrons for any element, just count from the left. Nitrogen is 5 elements from the left and has 5 valence electrons. Ignore the d electrons when counting valence electrons for Lewis structures. So here you have your group 1 alkali metals. They all have 1 valence. Alkaline earth metals have 2. We skip the d sublevel or the transition metals and we go to the boron family, which has 3 valence, carbon family 4 valence, nitrogen family 5 valence, oxygen family 6 valence, halogens have 7 valence, and noble gases have 8 valence, except helium has a full duet with 2 valence. Elements in the columns of the periodic table have the same number of valence electrons. The elements differ only in the core electrons, which have only a minor effect on the chemistry. Exercise 8.45. Write the Lewis dot symbol for the atoms arsenic, iodine, and krypton. And if we look on our periodic table, we see arsenic is in group 5A, which means it's going to have 5 valence electrons. Iodine is in group 7A, so has 7 valence electrons, and krypton is in group 8A, and so it will have 8 valence electrons. So usually the first 2 electrons are drawn as a pair side by side, and then afterwards we draw singles. So we have 1, 2, 3, 4, 5, and that would be all of the electrons around arsenic. We'll have our pair first, 2, 3, 4, 5, 6, 7 around iodine, and then here we'll have 2, and then it'll go 3, 4, 5, 6, 7, 8. So it really doesn't matter in what order you draw them in. It's just the first 2 are paired off, and then you're going to go single, 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 and then we're going to go pair, pair, pair. The octet rule in chemical bonding. The driving force behind chemical bonding is the desire for elements to achieve a full shell of 8 electrons. We are only counting s and p electrons in this. Electronegativity is a small measure of the pull on an electron from an element in a chemical bond. So the most electronegative element is going to be fluorine, and there is 0 electronegativity for noble gases essentially, and so as you approach fluorine you increase electronegativity. Fluorine has the highest electronegativity because it has a small radius, so the nucleus is more accessible. As the atom size grows going down the column in the halogen family, the atom has more electron shells. The nucleus becomes more shielded with core electrons and electronegativity drops. Going across the row towards the right, effective nuclear charge increases. The desire for electrons will increase from left to right. And you will be given a chart with electronegativity values so you don't have to remember them, and so it'll be easy to identify which one has a greater electronegativity. The point will be when comparing elements in a bond, for example in a bond between carbon and hydrogen, you would say, well, carbon has an electronegativity of 2.5 versus hydrogen is 2.1, and so because this has the stronger electronegativity, the electrons are going to actually pull a little bit more towards the carbon and away from the hydrogen, causing a partial negative, and this becomes partially positive, which you can see denoted with the plus at the end of the arrow tail. Here's your note card for this section. Be sure you can identify the number of valence electrons based on the location on the periodic table, and then draw a Lewis dot symbol by drawing a pair of dots and then every dot thereafter in singles followed by pairs. And you shouldn't have more than 8 dots total, because the octet rule states that all atoms want a full shell of electrons, and that's going to be 8 total, 2 in the S and 6 in the P. Electronegativity is the ability to attract electrons. Fluorine has the highest electronegativity because it has a small radius, so the nucleus is more accessible. And when you have more shielding, you decrease electronegativity, and the higher the Zeph is going to increase electronegativity. And this is going to be across the row, and this is going to be down the group.